Hey, how's everyone doing? We might have some people joining in, but if you're in the chat, feel free to say hi. Oh, got myself talking in the background. I need to stop those videos from playing so much. Let me end the MuBot and restart the MuBot. MuBot coming back here. And so this is a special office hours dedicated to coding in R and talking about some of the things we've been talking about coding this week and kind of giving some tips and tricks. Hey, Jesse, great to see you here. What questions do you have? We can take your questions or we can do mine. But let me know with what you're coding in R. This is dedicated to just coding in R. We can even do 201 in R. But MuBot is here now. We can say hi to MuBot. MuBot is in the chat, and we got some coding to do. So let's start it up right here. Let me talk about installing packages to start. Let's talk about installing packages. Okay, let's check that out. So you might hear me say something like install a package. So installing a package is a lot like downloading a video game. All we do right here, and we're in an R script right now. We've gone to File, right there, plus New File, R script. You'll see me have tons of untitles opened. So I'm just in a new R script, which is where we write code. It's basically identical to being in the bottom right here, but we can just write multiple lines of code, where on the bottom of this, if we write a line of code, we can't edit it. So the benefit of being up here is if you write something, you could then correct it and rerun it, where down here, you run it one time and it's gone, or you have to redo it. So we're just clearing off things to get a nice fresh environment right here to start off by talking about what is installing a package going to be and what are packages. Well, you can see what packages you currently have loaded up by clicking the following. The global environment is your kind of brain of R, but then you also have other things like loaded on, like packages. And the packages are right here, like reg class is a package. That's everything inside of reg class. Random forest is a package, and it comes with so many different things. Like, I believe these are data sets, and those are values. There's values, there's functions. Let's go to stats4. There's a bunch of values here. These are all these things you get. You get data. You can click at that data and look at that data right there. Whoa. Go over to reg class, and you got data sets down here. Where's the data sets in reg class? It's got data sets. I don't know why they're not there. All these different things right here are your packages that you currently have loaded up, and you probably have different ones loaded up. There's a data right there. There's values, and there's functions right here in this package in GG Animate. So, hey, Kaya, great to see you here, Kaya. So let's say you, Brian says, I'm using Plotly. And you say, Brian, I don't have Plotly. Now, how could you get Plotly? You'd have to install it. So Plotly is a package, and you type install packages. When you do install packages, you put in quotes because it's going to go search the CRAN server for the name of this package, and you type Plotly. Now, it is case sensitive. This won't find Plotly because I could put a capital P right there. It was smart enough to suggest, did you mean lowercase p Plotly? And you could just take this and copy paste that into there, and now it will reinstall it. I'm not going to reinstall it because I already have it. Now, once again, this is like downloading something. Here, we'll download Calce. Do I have Calce on this computer? Calce is a neat little function, or a neat little package. So I just downloaded the package Calce. So now that we've downloaded the package, which gives us a bunch of like different things, it could be functions, it could be data, it could be values. It's just a package of stuff that you just downloaded, like a program. Multiple things can be in it though. So download your package. A lot of times I highly suggest commenting this out because you cannot knit this. Cannot knit this in documents. We're not even in an RMD, but you cannot knit this. So I highly suggest commenting it out or deleting it. Now it won't run. It's just a comment. So it's not going to actually download or do anything because you only download things one time. But does anyone know in the chat for 100 points, how do I then load the Calce library? So when you load up R, it doesn't load up all your packages. How do you load up your Calce library? And then we're going to look at Calce, which is a cool, neat little library. So how would I load up the Calce library? How would I then... Close, Kaya, good guess with 100 points. Load actually loads .r data files, which are global environments. If you run the load, you usually use load for something like data.r data, and it probably will say can't find R data, no data file exists. So the library function, Jesse, worth another 100 points. This is for loading R data files. Might load other stuff, but I use it for that primary purpose. Library is how we load them. And notice how it's like auto-completing right there. So you download it using install.packages, and then you load it up using library. So good guesses there, Kyan. Good work. To get your libraries running, you have to run library And then I want Cowsay, not Cowplot. Cowsay. There we go. So now I've loaded up the Cowsay library, and you can see right there, Cowsay is the most recent loaded library. You can look inside of it by going here and see the functions. So I think animals, is that just a vector? Oh, that's all the animals. You say they look weird right there. So there is the animals, and that's how it's drawing them. But let's do Cowsay or say and say hello. And look at what we get when we run this. This is a little cat saying hello. Doof. No. It's a bat saying hello. Oh, spider saying hello. Buffalo saying hello. What is that? I don't even know what that is. Face cat. We can do face cat. Oh, look at that pretty unicorn right there. Face cat. Oh, it's a cat face. Hello. Say, I am a cat. Ah! I just closed out the pain. I did it quick key somehow. I quickly hit a key that did it. I am a cat by Catface. There we go. You're frozen. Oh no! Oh no. 2 seconds, let me fix that. I hit a bunch of quick keys really quick. 2 seconds. I'll probably unfreeze. Oh, that's horrible. I should never hit that button. Oh, there we go. Okay, good. Too quick, right? I actually hit my quick key that freezes my keyboard or freezes my screen. You're unfrozen, yeah. No, I've got quick. It's for the smash effect, which I'll have to use this semester. But it freezes my screen, and that's only the second time I've hit it. One time I really thought I broke my computer. But we got Catface right there. Thank you, Kai, right there, helping out. Be funny if I went a long time. I'm usually looking at the chat. I actually look at my confidence monitor not as often. But actually, I have the... there we go. Fix that. Oh, hey, we're good to go. So does that make sense? A little bit of fun, a little bit of craziness. You never know what's going to happen. But you load the library here, and then you get all your functions, and you can actually view what's in the library by clicking this. Usually we're in the global environment, to where if we store something like X is 5, it's stored in the global environment. Yeah, it's pretty fun. There's so many neat little things. Someone probably made a Snake game inside of R or something like that, where you could probably download a library of like little games. I bet there is. Let's find that, and then we'll do a new topic. But library of games in R. Someone has fun in games in R. Someone has to made this. It's on R console gaming. Explore R. Did someone make? Okay. Snake in R library. Package Snake. They might have 2020. Okay, so it might be package Snake. Okay, let's find out. Installed up packages. It's a classic game a lot of people make. It's... did you mean capital? Yep. Thank you for the advice. Just going to grab random things. Now we have to load it. And play Snake. Oh my gosh. Wait. Whoa. Press return to start Snake. Whoa! We're actually playing Snake instead of R. Let me go. Whoa! It's like on delay. I don't like this. I'm not this bad at Snake. That's such a delay. This needs to be improved. Oh, it's delayed. Well, okay, let's end the game. There we go. Game over. So someone actually made but this semester I'll definitely pop in. Awesome, Kai, anytime. So we got to play Snake inside of R because someone made a package called Snake. Definitely is not the best version of Snake I've ever played. If you've ever played that old school game right there, I've definitely played better versions that are I played better versions in the early 90s than this version. Oh, I swear someone Someone has to have made a better version than it in this in R, but you can actually view the code, which would be pretty cool. There's their code to play it. I would be interested. You can view a function by doing this, and I would be interested to see. Yeah, it's not that big of code. Put an image right there. So those are functions there. It's like doing it, column names. Is that where it's starting like the food or something? Cool. And there's the colors it's using. Pretty fun, pretty neat stuff. Field size, speed. Ooh. Oh, we got to try something here. Let's try this. Okay. Last thing we're going to do right here, and then we change topics. Speed equals 4. Oh, really? Whoa. Okay, I think it just like jumped to the end. Okay, that's a horrible idea. Well, snake function, you're not that cool. I've seen better functions, but you tried. So we were going to comment this out because we'll never use that again. We'll probably never play snake again, but pretty neat. I was hoping it'd be much cooler than that, but you never know. Let's change topics right here and talk about something else. So now that we know how to get these libraries on our computer, let's talk about some simple functions. And if you have questions right now, drop them in the chat. Let's talk about simple functions that we can use, base R functions. Base R functions. Okay, let's go talk about some base R functions. Let's do this. Okay, so you might be wondering, what do we mean by base R? Well, we just talked about downloading libraries and pulling up libraries, but base R means you don't need any libraries. If you have R, you have base R function. It's like at the base level. You don't need anything else. Everything else, Rock would say, it doesn't matter. You got it if you have base R, which everyone has. This is no libraries needed. We're using base R. Clear everything off right here and look at some base R functions. Now, when it comes to a base R function, they're pretty basic. Things like the mean is base R. It's not inside of any library. It's just going to be the mean, which you generally have. It comes with all R's. And so we could take the mean of a vector of numbers like 1 to 10. That's just going to be a base R function right there, such as like median also. It's in the stats package, but stats downloads with R. Sometimes the functions will say base on them. I think plot might say base on it. No, it says, wait, there you go. There's plot, it says base. A lot of these functions will say base, but stat downloads with R. I don't think you can get R without downloading stat. So I generally call it a base function. But a lot of times, if something is a base function right there, which means every R is going to have it, you're going to see base next to it. This is the package that a function is using, or the library it's using, excuse me. This is the library it's using, the base library of functions, where if I do something like visualize, you can see these are in library reg class. So noticing right there on the side of it, it tells you where that function lives. That came from reg class. So if you type visualization, unless you have the reg class library, you're not going to see this. But I'm pretty sure it's not possible to not get the stats library. So even though it's stats and not base R, it's base R. So median, once again, is going to get you the median of numbers. We could create a number vector right here of just different numbers. And the median number looks to be about, it's going to be, there's 5 numbers. So the middle number, that's going to be 3. There we go. I know how to get the median. So we have all these different functions. And what's really great is if we were to take a vector of numbers, like let's just say vector, and we were to ask people how old they are. So Brian is 40. People got 21, 20, 29, 28. We're just asking people how old they are. If you get to where you've entered in a bunch of data and it's getting too long right here, rather than going off the screen a lot of times, which I hate doing, it looks confusing, you can actually just hit enter right here and then start a new line, but it's also going to continue through. Now you have to do it after the comma, so you don't want to do it right here. That won't work. You would do it right here, and then you would be able to run the code. So that just keeps your code a little bit prettier. We like good-looking code right here. So that is the concatenate function, turning this into a vector of information, and we can view the vector by running it right here. I'm going to make this vector a little bit longer and just talk about the output you're seeing on the screen. So I'm adding more elements to this vector, just random ages, just typing in a bunch of numbers that are close together. So now we've added more numbers to that vector, and I want to show you what this means. This code right here, which I'm running by hitting Control-Enter on a PC or Command-Enter on a Mac, runs the code, and now we're viewing the vector. These are just vectors of a vector of ages people reported. Brian said he was 40. Someone said they were 21. Someone said they were 12. Someone said they were 114. These are just the ages people told me they were when I said report your age. Might work better if we call it age vector or something like that. So now it's an age vector, and we can view it just as age vector right there. Now, what you'll notice is there's no 1 in this vector. 1 doesn't mean someone's age. That means position 1. So the person in position 1 has an age of 40. The person in position 15 has an age of 23. Now, rather than going through here and searching through the vector, we can use this same sort of style right here to type in 18 and get the age of the 18th person. Notice how the square brackets pull positions. Now, we only reported back 1 position, but that is position 18. So it's the first thing being reported. It's not that they're in position 1 now. I guess they're in position 1 of what was reported, but they're still position 18 of the age vector. And we could see them right over, oh, they're 34. I think this is them right here. That looks to be them right there if we count and go to 18. We don't have to count though. There they are. They're next to 54. Yep. So that is the 18th individual or 18th element of that vector. Now, when we're talking about base R functions right here, what can we do with this age vector? Well, we can do things like mean, as we said earlier, and just take the mean of it. But check this out. A lot of simple to use functions like standard deviation, median, IQR, range, just take one, oftentimes take one argument. So we can take the median, the range, we could get a summary of this vector. We could get the quantiles, which will give us the 5-number summary of the vector. We could make a histogram of this vector. We could get a plot of it, which will give a scatter plot with the indices. We could do a box plot of this vector. And we're just changing this first thing right here. We could get the min of it. We could get the max of it. And these are all functions everyone will have by default. So all these functions right here just take a quantitative vector and return the output. Now, I say a quantitative vector, but they can take other types of vectors, but they'll do different types of output then, depending on the class of the vector. So these are all functions everybody has no matter what. So you can run the mean of a vector, the median, the max, the min, all these things right here. If you have questions, let me know. But these are some of your base functions, especially plot. Plot is used a lot because if you have another variable, let's go here to a base data set, the iris data frame. The iris data frame right here has something species because this is the species of the iris flower. So you see different species. I'll expand this a little bit here so we can get it on the full screen. So here's the species of the flower over on the far side, and that's a vector inside the data frame. So here's the iris data frame, and here's the species vector, just a line of information inside of it. And so now take a look. If we go to plot iris species, we will actually get a bar chart. Not the prettiest of bar charts, but there's our bar chart right there. Our bar chart, nice and easy. So if we give it a different variable that's quantitative, we'll get the indice plot. Little interesting pattern right there, a little flowy pattern. Now, what's going on right here is that these are different classes. The class is how R looks at an object and identifies what it is. So supple width is a numeric, meaning quantitative, where species is a factor. And you can better see this if we look at the iris data frame and see that these vectors right here are numbers, and over here we have categorical. Hence, these are numeric, like everyone here is a numeric vector, and everything over here is a category, so it's just category. You can also see it by looking right here and expanding, and you can see the format with the $ connecting the data frame to the vector inside of it to call it. So the species right here is a factor with 3 levels, and that just means 3 categories are used when describing the species right here. And there's a lot of other base functions we can use to identify this, such as we could go here to levels to find out what the levels are of species, and this will report the levels. Oop, graphic error. So there's the levels right there. Whoops, go away. There we go. And so we have Cetazoa, Versicola, and Virginicea. I don't know how to say those words. But those are the different levels right there to the species of the flowers. Other commands we can do with base R are things like unique to get the unique values, Now, this is actually going to give us the same thing right here, but if we did it on a quantitative vector, we see the differences between the output. So instead of doing it on a categorical thing like species, I'm going to do it on supple width, which is numbers. So this is just numbers right here. Now, numbers don't have levels, so we get null because there's nothing to report. There are no levels to a quantitative vector. Levels are only for categorical data, where unique can still be ran because unique is just going to tell us the unique values. It only reports each value one time, and it just reports each unique value. So unique can be really, really beneficial. What we could also do is we could take the unique right here and sort it. And now we have a sorted vector. So now we can see the unique values of supple width sorted from smallest to largest. And let's do a new segment right here and talk about functions and arguments and what those are all about. So let's head over here to the mind screen and talk about that. Okay, let's talk about some functions and arguments and what those mean. 22. So you might be wondering, what are functions and what are arguments? So a function just runs some pre-prepared code for us. Probably the easiest thing to do is if I just make you a little function right now. Functions can be made by the user by typing fun and then hitting enter using the snippet, which builds kind of a container to make the function for us. We give the function a name like hello world, and then we give the function an input, and we say maybe name right here, and then we do the following: paste, and then we say hello, and then we say name. There we go. That should be good right there. Give it a shot, and let's say hello world, and then let's say Brian. Hello, Brian. So this is a little tiny function right here, and let's examine what the function has in it. The function takes arguments. The argument is the instructions for the function. So when I put name in here, which is this name right here, it takes that and puts it right here. So whatever I put in right here goes right here. Like if I say Darren, it says hello, Darren. And it's just returning what's in here. And oftentimes functions have a return. If we're talking more about building functions, it's more about just how a function works. We have a return right there, which ends the function. You could even put in a number right now and it would say hello 5. You have to watch out though, because if we put in an object like Brian the object, it'll say Brian does not exist, because that's looking to run the object Brian to run that function. So when you think about this, we have a function takes a certain set of instructions. So let's think about the mean function, which is a lot simpler than this, even simpler than this little tiny function here. The mean function takes a few arguments, and let's look at it. Question mark brings up the help for any function we're using. So the mean has how many arguments? If you pause right here and look at this, how many different sets of instructions are there? Well, each comma separates out a new set of instructions. So the arguments are our sets of instructions, and the first thing that we input is, what are we taking the mean of? That's why a lot of times if I do the mean of the numbers 1 through 10, 1 through 10 right here, which is just a vector format of 1 through 10, 1 through 10 is x in this example. Like I'm just putting this here for the first argument. The other arguments right here have what are called defaults, so we don't have to enter in a value. So this code right here that I've written would run identical to the following code. I'm putting in the same defaults that are already running, but if you notice, that just runs the same thing. So we don't have to put these in because they have defaults. The default is when there's an equal sign right here, so it's already saying trim is equal to 0. If you're wondering what a trim is, that actually removes values on a certain end. Like let's say you have an extreme value. If we were to take numbers and we had values like this right here, and then we had like that big value right there, we could take the mean of our numbers, but notice how it's going to be inflated right there. So what does a trim do? Well, the instructions tell us down here that trim is going to remove values from each side. And so if I do like a trim of numbers, and I trim, let's say, 20%. It's a big trim. I probably wouldn't trim that much normally. You'll notice that 999 has been trimmed off because it's trimming off 20% of the values, about that much. So it's only taking the mean of these inner values right here, which you can see is about 4.7. It'll do it manually for us, but you're basically just cutting off and removing outliers on far ends of your distribution. So we call this a trimmed mean. And if you notice, it doesn't do a trimmed mean by default. You don't have to tell it not to do one. It'll just not do a trimmed mean if you don't make a change to the default state of the trim on the mean. NA.remove is used when there's NAs. So NA stands for missingness. And if you don't remove the NAs, you will get an NA if there are NAs in your vector. I think it does that because it's trying to alert you to it. So we're telling it right now, take the mean of numbers, trim off 20% on each side of the vector, like order the vector. So it orders it, removes 20% of the smallest values, 20% of the largest values to remove outliers. That's why we do a trim. And then also remove the NAs in the vector too. And you have to do that to get the mean if NAs do exist. And to tell it to remove the NAs, we're just going to change this to true. And now we get the same value we previously had because basically it's going in here and just removing this off. That's what it's doing for us in the background. So we're just saying, hey, could you knock off those NAs right there, take them out for us? And it's good to understand what your arguments do and which ones you have to input. The arguments you have to input are the ones that do not have defaults. Noah, it's so good seeing you here. Doing some helping out with R right here segments, trying to figure out what people have covered this week. And yeah, good to see you in the chat. Ask questions if you got them. So these are the arguments we have to put in, the ones that do not have defaults. Awesome stuff. We'll look at another function right here, IQR. IQR gets the interquartile range. And if you notice, type 7. Ooh. The type is the way in which mathematicians or statisticians have calculated these things. I think there's 9 types total. You actually have to look at quantile, I think, shows you the types. So we have to go to another one where it shows the different types right here and the 9 types, the ways these are calculated to get Q1 and Q3. I didn't know IQR wouldn't show that, but you would actually have to go over here to see how these values are calculated for Q1 and Q3, the 25th and 75th percentile. So when we look at IQR, it is going to ask us, it's going to use type 7 calculations by default. It's not going to remove the NAs by default. And then we have to input the value of what we're getting the IQR for. So that's what we're asking for the IQR for, a numeric vector of values, which just means you have to put in numbers. So now that we have this, we're going to type IQR of numbers. But once again, our numbers are going to have a missingness value, which means when we get the IQR, it's going to say it's missing. Oh, is it just going to get mad? Oh, it says error. And then it says, yeah, I think it's telling us. I haven't ran this one where it gives you that error. So let's change this to true, and it works. So true can also be written as T. Also, true can be written as 1. So a quick way to enter in your trues and falses is 1s and 0s. It works just fine to put in a 1 for true or a capital T for true, but do not write something like TRUE like that. If you notice, it was trying to autocorrect me, but I stopped it. This will not run right here. Yeah, don't do that. That is not the same. And you can notice by the colors, it's not recognizing this. This is the numeric 1, but also counts as a true. But this is the special character true, as is this the special character true. This is not true, nor is that, but it will try to correct you to the logical true right there so that it can run. So a function just runs a preset of code for us. It just is going to run this code right now in the background to find the IQR, which is 3. We could also find the IQR ourselves by going and doing the same sort of code right here on quantiles. And we could mathematically find the IQR right here, which is the range of the inner 50%, which is going to be 3, 6 minus 3. But it does that work for us. Like the long way to find this, which is not the end of the world, is to use positions and to say position 1, 2, 3, 4. That's position 4 minus, which is the thing in the 4th spot, 1, 2, 3, 4, minus position 2. There you go. And it is saying 75. So I'm going to use one last quick function on this called unname. Unname unnames the vector because this is a named vector. This just has a name over the position. That's not actually a value. I guess it is. It's in the name spot, though. So the vector just has names over top of it. Let's talk a little bit about vectors, though. That might bring up your questions. Well, what's a named vector? What's a regular vector? Let's talk a little bit about vectors right here. Here we go. Okay, another section right here about vectors and what they are. Just trying to put some stuff in here to help people out. What is a vector? What What is a vector? Okay, let's go check it out. So I was just talking about vectors and named vectors, and you might be wondering, well, what are they? A vector is just basically a line of information. So to create a vector, we use the C function known as concatenate. So I'm going to just call vector right here and store into it. This is going to store whatever I put over to the right side into that object right there. Now, this is a vector of length 1, which means there's one thing in it. But to make a longer vector, we have to like glue things together. So I think of this C right here as sort of like a gluing together of multiple things where I just start adding more numbers. And if you notice right there, it's a vector of length 4 now, which just says these 4 things are in a row. They're just like first thing, second thing, third thing, fourth thing. Just think of people in a line. It is one dimensional. If the vector does wrap around the screen, it's just because it doesn't have enough area to show you in a line. So these are just a long line of information right here. Like we could say numbers, and you can see the numbers right there over on the side of the screen are just in a line right here. It would just keep going. It's one dimensional. It's not two dimensional. Even if you look at the screen right now and say, well, wait a minute, this is a column and this is a row. No, a vector is just a one-dimensional data, just a one-dimensional array of data, just one line of data. So with this in mind, we can get positions in a vector. I've got 2 vectors on the screen right now. I've got numbers vector, which is the numbers 1 through 1000. I've got a vector vector, which is the vector of just numbers 5, 6, 4, 2, which is 4 elements. You notice the square brackets right there. If I go here to vector and I call position 3, that's how you get your position. It'll report 4 because 4 is in position 3. If I go to the numbers and I say go to position 99, it's going to report 99. But let's make a change. Let's make this go from -5 to 1000. So now this vector there starts at -5, and now in position 9 is 93. The first element of this vector is -5, and that's when I go here and I type a 1, it says -5. So that's the first element of the new numbers vector, which is a number sequence going from -5 to 1000. Now you'll also notice something, that vectors have classes, which is just the way R sees it. So you're wondering, what's a class? Well, class just means kind of the way R views it. Like I am class instructor. That's how I'm viewed in my class. I am the instructor of the class. Numbers is viewed as an integer vector. Vector is viewed as a numeric vector. Words is viewed as a character vector. Logical, giving some hints right here. Logical is viewed as a logical vector. So these are just different classes of vectors, and you can see the class right here. You can see how many elements are inside of it. There's 3 elements that just answer positions 1 through 3, positions 1 through 1006, positions 1 through 4, positions 1 and 2 of these different vectors. And there's one more I didn't mention right here. Let's say categorical. This categorical one right here is going to be a factor, and we'll say dog, bunny. Roberto, great to see you here. Do we also have double vectors? Yeah, so numeric should be double decimal precision, which in computer coding, so this is a factor right here. Oh, does it with 1 level? Oh, I didn't put my concatenate. We all make errors. There we go, with 2 levels. So now that is a factor right there. And Roberto, great to see you here. Let's make Roberto a mod. So with this, Roberto asked about double, and I'm pretty sure the vector right here, if we go to type of, there you go, it's double. That it is double. That's just kind of a little bit more about how R stores it. If you're wondering the difference right here, let's go look at type of and see what it's reporting. The function type of determines the R internal storage mode of an object. So you can see right here how R stores the object and how it views it with logical, integer, double, complex, character, raw, all these different types of storage, how R sees it internally. Also, someone else mentioned mode. I think one of my students mentioned mode in class, and mode is also another internal storage. I prefer to use class, which is kind of how R handles the object. It just lets it know, like, deal with this object this way. These objects can be used for these reasons. And you can also write to the class of an object. Be very interesting to see right here. What happens if we take class of categorical and change it to numeric? Oh, look, it did it. Well, that's your as.numeric. It's got attributes levels still on it. Good afternoon, Roberto. So it did change it to numeric, And then it also kind of appended on attributes. I don't use a lot of attributes, but attributes are kind of like, they're kind of like ribbons on a vector. They exist in the background on it. So that is a extra little thing on there. I think we can view with attributes. I so rarely use attributes. It's a base function though, so why am I not using it all the time? There you go. There's the attributes right there. And we could probably take just this from it. There's the attributes. I think we can... We could probably do this. Watch this. Now, boom. I deleted the attributes. I stored the null, which is nothing. I stored nothing into the levels of the attributes levels of it. So I deleted the attributes by overwriting it with the null vector. Null vector is a vector of no space. It is nothing, nothing. It's not that there's nothing there. There's nothing, nothing there. Where NA is nothing, missingness. One last thing to mention right here, so that's how you can delete things, is oftentimes overwriting it with a null. You can delete vectors in a data frame, or if you want to remove your vectors, you can do the RM to remove them, remove. But one last thing on this, we talked about named vectors just a moment ago. So named vectors. What is a named vector? Well, a named vector is just a vector with names over the position. I've got a, let's go to ages. And let's take the ages of Brian and Darren. No, he's had his, no, he hasn't had. There you go. And now I want to go to names of ages. And there are no names right now on ages. But what if I wanted there to be names on this vector? And names are just names over a position. So names are not actually values, so to say. I mean, you can use them as values, but they're kind of names for positions. And let's view what it looks like here. So Brian is the first position right there, and then Darren is the second. So now when I report ages, it says Brian 40, Darren 22. If I say ages of the first person, it says Brian 40. But now since it's a named vector, I could say age, and this is the benefit of it, age Brian, and it reports position Brian. Position Brian is position 1, but it's also known as position Brian. So you can use named vectors, and a lot of times we see it as tables. So if you go here and make a table from the Iris data frame of species, you could store your table as table. I do that a lot of times. And then go to position table, set to SOA. And there's the position set to SOA in the table. So it can kind of help a lot of times if you don't know the names of what you're working with or the positions or where things are at. It's like, oh, just go to this position by typing the name of it. So a table is actually a named vector right there. So it's really helpful with things like this, where if you're making a whole bunch of observations, let's look at, trying to think of a good data set. Data set empty cars. There we go. And let's see. It doesn't have categorical data. Trying to think of a base R data set. Data trees. What's in trees data? I've never seen trees data. Oh, look, it doesn't have good stuff. It doesn't have good stuff right there. Darn it. Swiss. I'm just loading different. Ooh, what is this? Interesting. Yeah. That's interesting. I'll check out that data set later. Well, we're not getting much with categorical. Last try. Sleep. Don't fail me now, sleep. Man, we're just getting quantitative all day long. Yeah, well. Oh, it's a time series data set. Neat, neat. Well, we showed the set of SOA one. Here, we'll do another topic right here. We might end soon here, but Boston has one category. Where was the Boston at? Oh, Charles River? Boston? Nice. There's no categorical in this one, I see. Oh, darn it. It'd be interesting. There's a lot of cool data sets here. A lot of interesting data sets right here to look at. R just has so much data. I mean, it's data analytics paradise right here. Let's see. Let's do. What are you wondering, Roberto? Let me know what questions you have. We'll do another thing right here. We've just been coding away. Trying to think what else people might need to know. Let's talk about logicals next. Let's talk about logical stuff. Okay, it's time to talk about logicals. Let's go talk about logicals. Okay. Logicals in R. Got the hiccups. When you're talking about a logical in R, you're talking about trues and falses. And probably one of the quickest ways to get trues and falses is to type ones or zeros. Ones and zeros, it's mad about me about that. But ones and zeros are just trues and falses inside of R. And we can prove this by going right here and saying true plus true, or true plus true. All of these lines of code evaluate to the same thing. So you can use ones and zeros as trues and falses inside of R. But what's the real benefit of this? Well, let's say I've got a data set of cars, empty cars, and we'll just call it cars. Empty cars is a data set that everyone has by default. It comes with base R. So we have right here, empty cars has been stored into cars. So how about this? Let's look at our cars and look at the miles per gallon that the cars get. There's all the miles per gallons of the cars. And now let's ask, do cars get 20 or more miles per gallon? Well, to do that, we're just going to add right here greater than or equal to 20. And now we can see yes or no, true or false. And this is a logical vector, as in the first car right here, it is true that the first car gets 20 or more miles per gallon. So that is a true statement. But what about, since they're ones and zeros, if we do a sum of the vector? Well, they're ones and zeros, right? So you can count them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Looks like 14, and I can count it, looks like. So now we actually just added up all the trues, and we just summed them up. Because remember, this vector right here that you see on the screen, well, it's actually the same. If I were to change it to integer format, it's the same as this. These two vectors carry the identical information. Even though it's trues and falses right here, you can just sum up all the ones, and you can do that by doing sum on it, by using the logical statement right here, and just taking the sum of it and finding out how many there are. But wait, there's more. We could go and take the mean of it and find the percent of trues. So what percent of cars get more than 20 miles per gallon? So this right here helps us do a lot of things very quickly by summing up trues or taking the average amount of trues, like how many cars on average, or like what percent, or how many total. And additionally, there's a few more tricky logical checks we can do. Okay, let's do a complex one. Well, the first one we need to know is equals equals. Equals equals means logical equals. It's not the same as 5 equals 5. That tries to store 5 into 5, and that's going to cause a problem right there. We'd want to store 5 into something like the word 5, or 5 into the word 2, but then you could confuse your friends by saying 2 plus 2 is equal to 10. They'd be very confused by that, but according to us right now, 2 plus 2 is equal to 10 because 2 is equal to 5. So we usually don't try to trick people like that, but that is how we store an object using equals. But now we could check if our value 2 is logically equal to 5, and it'll say true. So it is a true statement that 2 is logically equal to 5. The object 2, I should say, the object 2 is logically equal to 5. But what about some more complex ones? How about %in %? This means contained in. So when you see %in %, you're asking, is 2 contained in 5? Is 2 contained in 5? I'll try to read a sentence. And the answer is no, 2 is not contained in 5. But is 2 contained in the vector 2, 5, 6? And the answer is yes, 2 is contained over there. So we're asking, is this thing right here contained over here? We can do a little bit more complex by asking, is 2 contained over here? Is 4 contained over here? So now we're asking two questions because there's two things on the left. Is 2 contained over there? Is 4 contained over there? That'd be true and false. And that's how we evaluate these things. But what about this? Is 4 contained over there? Is 2 contained over there? That's going to be false true. Why did I do this? Because of this. This is very different. This is a logical check to see if elements of one vector are equal to elements of another vector. So the difference here is instead of asking, is 4 contained over here, is 2 contained over here, we're asking, is 4 logically equal to 2, is 2 logically equal to 5, is 4 logically equal to 6, and then we'll get a warning saying they're of different length because it didn't fully go through the vectors equally. So we get false, 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 because 4 is not equal to 2, 2 is not equal to 5, 4 is not equal to 6. It does it by order right here. So we could switch the order back, and we'd actually get a true at the start. If we go put a 2 right here and a 4 right here. So is 2 logic equal to 2? True. Is 4 equal to 5? No. Is 2 equal to 6? No. And we can confirm, we'll put another 4 here at the end, because now at the end it'll check 4, and we won't get the error of different length vectors that we're seeing down here. So now we get a true at the end because it says is 2 equal to 2, is 4 equal to 5, is 2 equal to 6, is 4 equal to 4, and you can see the logical checks down here as it went through and did those. 2 equal to 2, 4 equal to 5, 2 equal to 6, and 4 equal to 4. Those are the logical checks right there. But let's see here. Let's see if there's any other questions. This is working with logicals inside of R right here. There's so much we can do with logicals. So much we can do. But we'll see. I'll tell everyone tomorrow. I'll be like, it's the big thing. We might need to do some Friday office hours. There's some big assignments due this week. Some big assignments. And we'll see. Roberto, great seeing you here. Noah, great seeing you here. Kaya, great seeing you here. If you don't mind, tell me out. I've got an issue with vectors. I'm trying to create a character vector based on the values of an already existing column. Oh, cool. Is it for our classes, Roberto? What are you working on? Let me know, Roberto. Which one are you working on? For example, age column, I need to create a new vector called adult, which has yes if age is greater than 18, else no. Exercise, cool. So what we would do right there, here, watch these steps right here. You ready? So we go to something like empty cars, and we want to create a new vector, right? So let's call a car cool if horsepower is greater than, what's horsepower? Like, what's a good horsepower? So horsepower greater than, let's say 180. Okay, so these cars are going to be called cool. Does that make sense? Introduction to statistical learning, cool. So I'm going to do an example kind of like it, and then I want you to think how this applies to get an idea of what to do. So this is not exactly your problem. I'm not working the exact data, but I'm checking to see if the horsepower is greater than 180 of a car. Does that make sense? So a logical check right here. And then let's do the following. Let's go right here and go, if horsepower is greater than 180, let's run the code cool. Does that make sense? Else, let's run the code not cool. Oops, I made a mistake. What did I do? Oh, run the code. Horsepower greater than 180. What did I do? Condition 1. Oh my gosh, I totally messed up. If else, my brain broke. We'd have to use a loop for that. If else, if horsepower is greater than 180, cool, not cool. Not cool, Brian. So these are the cool cars right here. We have, if the horsepower is greater than 180, we're going to say the car is cool. If the horsepower is not greater than 180, we're going to say not cool. Now, you could nest it. We're not doing any nesting right here. We could say super cool. Like if horsepower is greater than, let's say 220, it's cool. But now, let's say super cool. And now let's go into this function right here and nest something, go if else. And we're just doing another version of this where now we do an additional check and then we put not cool. So this is a nested version now where we have our cool cars. Here, we need to go 180 right here. There we go. We have cool cars, super cool cars, and not cool cars. So the if else allows you to evaluate things. Very simple version of this would be if else. If else, the numbers 1 through 10 are greater than or equal to 6, then they are large. If not, they are small. And that's just a quick version of that. Does that make sense right there, Roberto? Now that you have this created, let's just store this as X. And if you store it as X, we can go here and call this a factor. So now we have X as a factor. It's going to be a categorical variable. So far, so good. Awesome. And now that you've got a categorical variable, you can go to your car's data frame and create a new variable and let's say coolness of car and write in the coolness of the car. And what have we done? we have added in a categorical variable at the end right here. So this is how you can do it right here. You want to do a logical check right here with something like an if else, and then go right here and add in, turn the class of it into a factor, write it into your data frame, and that's how you would do things right there. So just checking. Now you could do it with a loop on an individual's age because you're calling like age of an individual right there. But I would use an if else right there and then use the assessment of it. So understanding the if else is very important. How if else takes like a letter vector. Let's take letters. And let's say if it is equal to A, we'll say this is A. And if not, other letter. So now it's going to convert my letters vector into this is A, else it'll say other letter. So understanding if else is super important, it's super powerful to kind of point out. We could say like, you know, R, like this is R. And there you go, this is R. So it's just showing you the position of the letters vector. Wouldn't super need this, but that's just turning it like other letter. This is R. Or, watch this. If the letter vector is contained in the vector B R I A N has my name. And there you go. There's B, and then R's over here, right? R I A and N. No, wait, I's over here, I think. B R I A N. No, B R I A N. There we go. So the %I in % is contained in. So if the letters are contained in Brian, then it's going to say has my name in it. And yep. So that's what we have right there. If the letters are contained in Brian, there you go. It's checking each one of those. Is A contained over here? Yes, A is contained over here. So it runs this code. Sometimes I parse this out a little bit further too to make it look like that. But Roberto, great work. That's going to end our office hours for today. But thank you for asking about the if else and how to use it. It's a very powerful function to use if else. It allows us to recode things. This is currently a character vector. Make sure to always understand the class of the object you're working with. If we check the class of this, this is just words right now. But you could take working for statements like Python-esh. Thank you, Professor. Awesome. Well, good work. Yeah, keep practicing, keep asking questions. How would we do this? Make sure to check the class of your objects. If you overwrite it with a factor version, it's going to be a factor. And then when you recheck the class right here, it's a factor, which means R handles it differently. It has levels, as you can see right there. But that's got it. Roberto, excellent work. Good seeing you around. We're done for today. Bye.